over. Another person wants submitted. Okay, we should be going here, and Luke is making too much noise, so I see Luke's name, not my picture, and that's the wrong picture. So, okay. System. Okay. Now I can see what you guys see, I think. Okay, what you're amazing. We might actually have a classroom today. I set this up so that when I'm standing like you see me in front of things, you can't see my head and so forth. That's because I'm trying to make the background more visible. Okay, so you guys will have to yell out at me at home because I may just come up to read the book or something and then blocks out everything. Okay, today for the first time, we have 3, 5, 9, 10, 11 people here. That's a new record, I think, for this semester. So I put up on the board what you can see there, and hopefully that's better than it used to be. And what you guys can't see off the screen, I've written some other things that people in the class can see, but I don't want you guys at home to see it yet. And I don't want them to think about it, and I just ruined that because now they'll all think about it. Anyway, what you see with L'Hopital's rule is something that's missing in all of these things I listed. These are examples in the book. I didn't put down all of them, but they're examples, all right? And in all the problems, besides in the section in the exercise, all have the word limit in front. L'Hopital's rule is about limits, and it's about things called indeterminates, of which I listed a few of the things that can happen when you, let's say, without checking, just stick stuff in, hoping that if you just stick numbers in, wherever you're heading, if you're heading toward 1, just stick 1 in and you hope everything makes sense. All right, we have rules about such things. All right, for example, the limit of a quotient is the quotient of the limits, meaning you can take the limit of the top and the bottom if both of those limits exist and if the limit of the denominator is not 0, for example. Well, so in all of these cases, if I would put the word limit in front of any of these, depending on what I put underneath it, like if I write limit here, you can still see that. If I write limit here, whatever I put under here would determine what I do over here. Both the numerator and the denominator are continuous functions, except the denominator is 0 at 1. As long as I stay away from limit 1, I can put the number I'm heading toward into the formula, and that's the answer, because we have continuity. If I put infinity in there, that's a different problem, okay? We have talked about x's going to infinity, but that's a different problem, but we've considered it. So in this particular case, when you do that, you will get what's called an indeterminate case. And that's what we're looking for to solve by L'Hopital's rule, because if you put infinity into this problem, you would get infinity over infinity, which would be a questionable thing. And that's kind of where L'Hopital's rule would come in. However, for the example, what the book puts underneath here is 1. Okay, the place which you hope it wouldn't put because it's harder to do when you don't have the thing continuous in a numerator and denominator. Okay, so this requires something besides just stick the number in. And that's where L'Hopital's rule comes in. Now, if you go ahead and stick the number in anyway, because we tend to do that, the log of 1 is 0. And x minus 1 when x is 1 is 0. So what you would get if you did that is this kind of arithmetic, which you're not supposed to write. This is called an indeterminate case, meaning we do not know how to simplify that because sometimes it might be 5, sometimes it might not exist, sometimes it might be infinity. It depends in a way when you're taking this x approaching 1, so to speak, it depends on how things approach up here and how things approach back down here as to whether or not the ratio exists, is infinity, is 0, whatever. It can change depending on what you're talking about here. Okay, both of them can go to 0, but much different speeds, quote unquote. And therefore the ratio might go to 0 or might go to 5. All right, so that's where L'Hopital's rule comes in. Now, this is a review, not a repeat. Okay, we can prove that if the derivative of the numerator, and this is not the quotient rule for derivatives, the derivative of the numerator and the derivative of the denominator independently, if those, when you head to the same place, if those two have a limit, then you can write equal here. So in this particular case, I think the limit is 1, and the question is there a bridge here? Okay, one can always do stupid things like that. It doesn't turn out to be stupid in this case. One can always just say, oh, I'd like to just differentiate that one and integrate this one. Okay, great, I'm glad you did, but what does it have to do with the problem? Okay, all right. Well, in this problem, it turns out that here's a bridge that you're allowed to cross. And it gets you out of the problem of what to do because it's a solution, so we did it. So basically, when you have indeterminate cases, when you have things that you shouldn't write, that come up anyway, L'Hopital's rule gets you out of it. Now, there's about, and I didn't count them, there's like 18 L'Hopital's rule. Why? Well, because we can approach 1. We can approach 1 from the right or 1 from the left, because that makes a difference. And what the people in the room can see over here is I wrote some things here, and you can't see it at home, but I'll say what it is. We have some cases where the limits go to 1, limits go to 0, limits go to 0 plus, meaning on the right, pi over 2 minus, 0 plus again. That's because these here are the limits that are attached to these examples, okay, which I just wanted to keep away from temporarily. So, for example, I can write here, limit as x goes to 1. All right, if I do that, I got no problem. Denominator goes to 1, numerator goes to tangent 1, whatever that is, I don't know, but it exists, minus 1. It's just some number. So that's not what the book does. The book writes here 0. Now we've got a problem. Okay. Now, it might ask us to do 0 plus, it might ask us to do 0 minus, or it might just say 0. So there's 3 cases. So for each thing you have over here, we have for every number, left, right, and both sided. Okay. We also can go to infinity or minus infinity. That's 5 cases. All right. And we also have different situations that come up that are indeterminate. And so when you kind of write all that down, you get 15 to 18 cases, depending on how many hairs you want to split. But all of them say, differentiate the top and the bottom, see what you get. Now, so if I do that here, the derivative of tangent is secant squared, derivative of x is 1, this is 3x squared. Now, L'Hopital's rule says that if this limit exists, going to the same place, they're equal. And remember, that's that bridge. The trouble is you look at this, and this is better than the what? It doesn't seem to be any better than it was. It actually is better. But we need to determine whether this limit exists, and it's a new, perhaps a new L'Hopital's rule problem. Because if I stick 1 in 0 in here, the numerator becomes 0 and the denominator becomes 0. So I have another L'Hopital's rule problem. So I could differentiate the numerator, differentiate the denominator. Again, take a new limit and see. Now, I don't have any room here. That's good because I don't want to do that. If you differentiate the secant squared, you're going to get a mess. I mean, it's 2 times the secant times the secant tangent. So that's 2 times the secant squared tangent. That begins to sound like things I don't want to deal with. So in this problem, and in general, in all limit problems, you always see if you can simplify things before you take the limit. Okay? Well, is secant squared minus 1 something you can simplify? There's a Pythagorean relationship that I memorized as secant squared minus tangent squared equals 1. So that would mean secant squared minus 1 equals tangent squared. That's one of those trig formulas that you better know real well by now. And if you don't, there's a form of stuff in the back of the book to learn, and you better be learning it sooner or later because it's sooner or later going to kill you. So I can change this, because I'm out of room, to tangent squared. And why is that a good thing? I'm going to look at this now, and I can write that as, again, I have a problem with space. I can write that as a third of tan x over x, that's not very big, squared. What happens to tangent x over x as x goes to 0? It goes to 1. You're supposed to know that. So without using L'Hopital's rule a second time, by changing the algebra, I can see what this limit is. It's 1/3 if I didn't make any other mistakes. Okay? Now, in this case, you could have done the L'Hopital's rule. Sometimes, and you always need to check, but the first idea is simplify. Second idea is L'Hopital's rule still applicable? Okay? And people mess that up because they get to like this idea and they keep doing it until it gets real simple. Well, sometimes you go past the place because it has to be one of these situations for a limit every time. And if you don't look at it, this may be 0, but this may be 1 or something. And then you can't use L'Hopital's rule again. All right. So now, L'Hopital's rule is built, as I said, it's like 15 cases or so, built on what this number, not what the number is, but whether you're heading toward a number or the right-hand side, the left-hand side, or plus infinity or minus infinity. Okay. And this is mainly built on 0 over 0 or infinity over infinity. And it can be plus or minus or plus or minus and so on. There's 3 different kinds of plus and minus infinities. This is where I told you get the 18 cases. Okay. Now, this one is not a L'Hopital's rule problem, but this one is a L'Hopital's rule problem. Now, on the recording, for people who stopped the recording now, it just sounds like I went nuts because I did. I said 2 things that can't both be true. The point is, it's not in the form of a L'Hopital's rule problem because we only do L'Hopital's rule with quotients. And we don't have a quotient, you don't have L'Hopital's rule. However, we have a product. Products can be made quotients. So what we do with products, if we want to use L'Hopital's rule, and this particular limit, by the way, is, if I look at it right, is 0 plus. So we're heading towards 0 plus. Now, why the plus on the 0? Well, because logarithm isn't defined for negative numbers, and therefore you can't approach from the other side. You can only approach from the right side. That's why somebody stuck plus here, namely me. Okay? But we can't directly apply L'Hopital's rule. If L'Hopital's rule says differentiate the numerator, differentiate the denominator, we ain't got any. So we got to change things. So can we change things? I'm sorry about limited space here. We either write this like this, there's a nice quotient for you, or we write things like this. There's a quotient. Now, which one would you rather differentiate, numerator and denominator? Neither one of them is particularly wonderful, but which one would you like? I think the first one's easier to differentiate than the second one. Therefore, I would try this one. And when you differentiate the numerator, now, as I say, my problem is space here. When I differentiate the numerator, I get 1 over x. When I differentiate the denominator, I get minus 1 over x squared. Okay? Now, that's good because I can simplify that complicated fraction and just get minus x, I believe. And that I can take a limit of. Okay? So that's another way thing here. But you have to play with it. And what's this one? This is the difference. Okay? And the problem in the book is the limit as x goes to pi over 2 minus, because evidently pi over 2 is a place where things happen, the tangent and secant. Okay, on one side they're one thing, on the other side the other thing, because they go to infinity and stuff. So you need to change this somehow. So what do we suggest? Secant is 1 over cosine, tangent is sine over cosine. That's 1 minus sine over cosine. Now I got a fraction. Okay, and that's the game that you play here. And the last game you play, the author plays checkers and I play chess. Okay, the author might disagree, but he's dead, so nobody cares. Anyway, how do you deal with the last kind of thing? Because where we're heading in the last kind of thing is to 0 plus. So the cotangent is 0. I don't know what that is. That's some kind of infinity thing. And the sign here is 1 plus 0. So I got kind of 0 to some kind of plus or minus infinity thing. Sounds like a L'Hopital's rule thing I might try. So when you have powers, and by the way, this is the same kind of thing. I have x to the x power here. Okay. What I recommend you do, which works for me best, and you don't have to, you can follow the author. The author, you know, he was Canadian, so he knows more than I do. If we remember something that I think you need to remember anyway, a to the b power is defined as exp of b natural log a. That's the definition of power. Okay. So 1 plus, this stuff is visible, yeah. 1 plus sine 4x to the cotangent x is the exponential of cotangent x times the log of 1 plus sine of 4x. And it doesn't sound like I made it easier, but actually I did. So I've rewritten this as exponentials and logs. What the book does is takes the log of both sides, doesn't have both sides yet, but takes the log of the left-hand side, and that brings the cotangent down. So the log, when you have an exponent and you take the log of a thing, it puts it out in front, if you remember. Well, that's exactly what this does. So we're really doing the same thing in a little different order. Okay. If I rewrite it this way, what's the, this is not, oh, shoot. It's not L'Hopital's rule. Who ever heard about all this stuff? I mean, L'Hopital's rule is supposed to be about fractions. So I don't have a fraction. But I'm going to hang and I'm going to just do this so that I save some space, I'm going to put a limit right here on this problem. And I'm going to put a limit right here, and where you're heading in this case is 0 plus. So the limit of the problem, the one we're trying to find, is the limit of all this new thing. But the exponential function is a continuous function. If this limit is going to exist, this is like limit of f of x as x goes to x naught. What's continuity? Limit of f of x as x goes to is f of x naught. You get to stick in where you're going. So if this is going to make sense, and right now that's a question, the answer will be the exponential of the limit of the cotangent and the rest of it. So because the continuity, again, what continuity does is allows you to interchange, if you think about it, the order of limit and function evaluation. Because if the function's continuous, this will become x sub 0. I get it written right. The limit of x as x goes to x sub 0 is x sub 0. This is f of x sub 0. So if you look, this is the limit first, then it evaluate. This is f first and limit. So continuity allows you to interchange two processes. That's the idea of continuity, to be able to take this thing you're doing inside. So if this makes sense, the limit of the exponential function will be the exponential function of the limit. Okay? Now, and again, we shouldn't just do this. This is what we will do. We go ahead and do it. But we ought to do the last part first to see if it exists. And then if it does, then we can do all this. Because this only, that's why I put the question mark. Because this only works if the thing in the end has a limit. Okay? Well, what do I got over here? I got a cotangent times. That's like this earlier thing. I had an x times. Cotangent times what? So what did you do? Over here we put, instead of x in the numerator, put 1 over x in the denominator. What do we do here? Instead of cotangent in the numerator, I'm going to write same numerator log thing. I'm going to write tangent in the denominator. Now I got a fraction. And now I can test L'Hopital's rule. Okay? So when you go to 0, is tangent 0, 0? The answer is yes. Is log of 1 plus 0, 0? The answer is yes. Log of 1 is 0. I have 0 over 0. L'Hopital's rule is applicable. I can take the derivative of numerator and denominator, take a limit, see what it is, take that number, stick it in the answer, and take the exponential of it, and that's the answer. Okay? Which we'll do, but I just want to. So the derivative of the numerator is 1 over this thing I don't like too much, it's too complicated, times the derivative of the inside, which is 4 cosine 4x, I believe. Okay. And the denominator is secant squared x. Now, I want to take that limit as x goes to 0 plus the secant of 0 is 1. That's great. Exists. No. So what about the numerator? Cosine, this 0, 4 times 0 is 0. Cosine of 0 is 1. Sine of 0 is 0. 1 plus 0 is 1. So this goes to 1 over 1 times 4 times 1. That is 4. And the denominator is 1. So this whole mess here becomes 4. And we have exp out in front of it. And so what is the, so this exists, and therefore this is okay. And the answer is to this problem here, e to the 4th power, if you'd rather write it that way. An unexpected thing. I mean, when you see this problem, I don't know what you expect, but I don't think you would guess this, okay, in your wildest guesses. Because it's got sines and cosines. What the heck did the exponential come from? Who knows where it came from? Okay, so that's that game. And I erased x to the x. How would I do x to the x? It's in the book. I think we need to move on. X to the x I write as the exponential of x log x. Wait a minute, exponential of x log x. I got x log x here. I know what it does. So as soon as I write it as the exponential of x log x, and I take the exponential of and try it inside, it's going to be 0. So this is going to be exponential of 0 is going to be 1. Do it in my head. Since I already did this one. Okay. So x to the x, which is a horrible looking function, turns out to have an easy derivative if you just remember about this one. Anyway, anybody at home have a question? Anybody here have a question? Actually, I have a class. Okay. Other thing I can do here, I can't do when you kind of, I mean, I can't hide the people here, but I can hide from the people at home. They can't see me right now. There's nothing on the screen except the blackboard. I can make mean looks at the people at home and nobody knows. So anyway, fortunately, I'm too big a person to do things like that. But I hear nothing from the peanut gallery. I'm not sure which of you is the peanut gallery, but I hear nothing of any complaints, questions, thoughts, whatever. So please look at these examples. You're supposed to know about them already. I suggest highly that you do some problems, either in the book or WebAssign. Oh, I've still forgotten to put up the WebAssign problems. I meant to do that this morning, but this morning I was informed about, when I turned on my stuff about 8 o'clock, that I would be no longer able to receive emails because I exceeded my limit or something. So I don't know if it was a real letter to me, email or not, but I spent the next 2 hours after that simplifying my emails and had planned to put it in WebAssign this morning, but just didn't get to it. So I'll still get to it, I guess. I don't know, still try. Okay, so the other thing to do in the exercise, because we're going to have a test on this stuff. Okay, and it's not going to be an exhaustive test on this stuff. So there won't be very many problems, but that means each one will count more. So you want to make sure you can do them. It won't be difficult, but you don't want to mess those up because that might be 20 or 30 points, even though there may only be 3 problems. Maybe it's 10 points a problem or something, but you don't want to miss them. So I would suggest you go through the true false quiz on page 504, because you may remember, those who were in my class, that when we did a test on this, I used the true false quiz or part of the questions on true false question thing. And I might do that again because some of you never got them right. And I might do that again. Or I might just go to the review. The review is where you have the whole chapter, which we didn't review, but you're supposed to be accountable to it. And so there's questions you can get, there's integrals. And so the review section is a nice section. And I will be putting a bunch of problems on the board on WebAssign when I remember to do it. So when do you want to test? And how do you want me to test you? 1 by 1, some kind of torture chamber. You want to be waterboarded, whatever. Might be fun. I've never done that to anybody, so it might be fun. For me. How many days? If we have a remote test, we could do a test in WebAssign where you do so many problems I choose, not like pick 10 out of 70 or something, but where I just make up problems and put them in WebAssign. We could, or I can make up a test from the book, or from what we did. And then this question you should be worried about is how much of those notes is going to be on the test. And I'm not going to answer that yet, but because I want you to read the notes. Anybody have any comments from either here or there?
Will the test be open noted or not?
I'm sorry, say again?
Is the test going to be open notes or not?
I don't know. Can I trust you?
Yes.
Would anybody dare say no? Can I trust you? No, I'm going to cheat, man. The problem is integrity, okay? That's the problem. Last semester, we had some people who were a little bit loose with the rules. So I would like to make it a closed book test, but I don't know how I can enforce that. Certainly I can enforce it. I can set a deadline and have you proctored. I mean, there's all kinds of things we can do. Okay. We can have, you have to have a video and I watch you take the test. And I wouldn't do it, but I have a secretary do it. And we can nail down as much as possible some kind of security arrangements. I would like to just say we trust you and so forth. We could say that you have a certain time limit to take the test and you would be on your honor to be within that time limit, for example. Or we could say, you can take 12 hours to do it if you want. I don't care. The question is, how do you see what a test is really for is to get you to learn. And the second part of the test is to prove to me you learned something because I got to make up grades. I don't care about that so much. I want you to learn stuff. So we can do anything you want to do as long as it's fair and equitable and So I suggest we have some kind of test next week, not Monday, because that would cause some gray hairs to grow in your body somewhere. Anybody? You want an in-class test? We have somebody, no, I don't want an in-class test. So you want a remote test. What about a test on WebAssign?
I like the test where you can write things out.
I can't.
Yeah. I like the tests where you can write things out on paper better.
Right, well, you could do that anyway. You could take the test on WebAssign, but write them all down and submit it. That'd be possible. In other words, the test could be on WebAssign. You could do it by hand. That's possible. It just depends on how I deliver the test to you. I could deliver it by, put a test on Blackboard, that's so many questions, or I could do the test from WebAssign and then you could answer it however you wanted.
Personally, I think
I would say towards the end of the week, we ought to be taking a test. I tend to allow you more time. So to me, as far as I'm concerned, you can have a couple of hours or something. And whether we nail that down or not, we'll have to figure that out. Yes.
Will the test be over the vectors and the
Yes, the chapter 12 stuff and chapter 6 and the notes. We can talk about what's on the note test. I would require you to know from the notes maybe Monday. Okay, so what I want to do is look at the stuff, maybe tell you more tomorrow. I want to look at whether I think there's good problems in WebAssign to ask you or whatever. So I'll tell you much more about it tomorrow. We'll kind of nail it down. Okay. In the meantime, what I want to do is talk about chapter 7. Okay. And that's okay because they may or may not be okay. But the point is that you have learned how to perform integrals either by remembering that when you did a derivative, you got a certain answer. And now we have the answer and we're asking you what's the antiderivative. And because you remember that, you remember that you went from A to B. Now we got to go from B back to A. Except we have to add a number C when we do that, when we find antiderivatives. All right, that's one thing. So if I had the secant squared and I say integrate, you say tangent plus C. If I say integrate tangent, you say secant squared plus C, because that's what about 45% of you will do. That's wrong, because the derivative of tangent is the secant squared, not the integral of the tangent. Okay, so people get confused about that because we're going back and forth. So to just say what an antiderivative is, you have to know what the original function was that you differentiate. And you didn't integrate tangent yet. Okay, now we might have, but that's because we know a trick. Anybody know how to integrate tangent? Integrating sine is easy, it's minus cosine. Integrating cosine is easy, it's minus, no, it's plus sine. Got to be careful. You should hesitate like I did and say, is it plus or minus? Oh, okay, I remember. Tangent though, what we do is with tangent, we change it to sine over cosine, and we use the only other thing we know if we don't know an antiderivative, we use integration by substitution. So we need to review integration by substitution because that's the first thing that you should think of when you see a problem for which you need to find an antiderivative or a definite integral. That's, I think, in chapter 4 or 5. Okay, so one of the things I need you to do over the weekend is to go back and look at integration by substitution in the text. And to point that out a little bit, as I said, for tangent, one of the things you learn when you do this chapter that we just got through is that this particular antiderivative, this is one you're supposed to know. Okay, so if I had that to do, I'm supposed to just say, oh, I know what the answer is, and write it down. If I have sine over cosine, that's tangent. Now, never, ever do you do L'Hopital's rule backwards. Never. Okay. In other words, you don't say, oh, I know the integral of sine and I know the integral of cosine. I'll just do that. No. Okay. Also, some of you, I hope you learned all, the derivative of the tangent is not the cotangent. Okay. There's things like that that shouldn't be in your mind. They may have been in your mind when you first started, but you should have gotten rid of it before now. What you do here, or what most people do, they abuse the notation. They look for something where the function is there and its derivative is there. And if I look at sine, derivative of sine is cosine. Okay, that might be what I do. Or I look at the derivative of cosine and it's minus the sine. Well, I don't have a minus sign, but I can make myself have a minus sign if I want to, by putting in two minuses. And so I can, if I want, let u be cosine of x, and then what people write, because of the abusive notation that we use, people take what are called differentials, which means a derivative. And once you get the derivative done, you stick a dx on it. And the idea here is to replace everything you can see here with this new stuff. And if I do that, the minus sine x dx becomes du, and the cosine x is u. And so I've transformed something I didn't know about to something that, this looks kind of familiar, I hope, because it's answered up here. Now, up here we have x, down here we have u. But inside this environment, this is the same as that. In other words, in terms of this integral, we say these things are dummies. Now, actually, u is cosine x, not x. But once I see this, I'm supposed to think this. And so the answer here is minus the log of absolute u plus c. And then what you do in this process is you go and stick back what u turns out to be, which is cosine x. And so you get the final answer, or more or less, minus log cosine. Now, some people, not me, but some people write log absolute secant. I don't, but some people do. Why is that? Because minus for log becomes a power. And this is reciprocal, cosine reciprocal is secant. And so some people write this. I don't like this myself. There's other problems with this. With cosine, we know much more about it than we do this one. This one only exists in certain places and stuff. It goes to infinity in certain places. And so it's easier to see this, I think. But it's not wrong. It's just a different variation. But what I really hope to show you here is one, about the dummy stuff. And two, we try to figure out something to substitute for which the derivative is there as well. And that's the concept of integration by substitution. You guys need to go review that. Okay? So now, so when we were at the end of the semester, last semester, I could give you a final that had integrals on it. And the integrals you either had to just kind of figure out because you remember antiderivatives, or you had to use substitution. That was all we had. Okay, so for example, there were certain things we couldn't do. I mean, it just didn't work. For example, suppose I have x times cosine x. Okay, you can see that almost.
Now again.
Now you can see it. Thank you. Suppose I have this to integrate. Well, you can substitute all day. You're not going to get anywhere. And most of us are, maybe some of you are, but most of us are not clever enough to say, oh, just take so-and-so. I know the answer. Does anybody know the answer off the top of their head? Can you just stare at it and know what the antiderivative is? Okay. Well, that's nothing bad for you guys. I mean, nobody can, okay? And if there is somebody that can, that's great. I'll give you another one and we'll see how far we can go with this. But I'd like to find out how good you are. Okay? There are people who just stare at these things and they know. I've never been one of those people, although I try to act like it sometimes. So if I know the answer, I say, oh, you just, you know, and it really makes me look smart. What it means is I spend an hour trying to figure it out before class. Okay. Anyway, this doesn't work. Well, unfortunately, okay, what did the substitution involve? Substitution involved putting a function or seeing a function here somewhere. And it actually turns out that substitution, when you introduce it, you're talking about inverting the chain rule. You're going back in the chain rule. The chain rule says, if I'm differentiating f of g of x, I differentiate, I get f prime of g of x and g prime of x. And you have an inside function here. And so if I had an integral here and did substitution, I'd be substituting for the inside. Integration by substitution is trying to go backwards in the chain rule. Okay? So it occurred to somebody at one point, what other differentiation rules do we have? Well, we have a product rule, quotient rule, sum rules, and so forth. The sum rule wouldn't be very good here because I don't have any sum. I've got a product. Wonder about the product rule. So let's write, if I have the product of f and g, not the composition, I've got little room to write here, but the product rule says differentiate the first, leave the second alone, plus leave the first alone, differentiate the second, right? That's called the product rule. I wonder if I can somehow use this. See, the left-hand side, if I had to integrate the left-hand side, that's easy. The integral of fg prime is just fg. So here's the game. what we're gonna do is we're gonna take one of these two to the other side. And so I'm gonna, and it doesn't matter which one, it's just, if I let this one be on one side and this be on the other side, then this would be what I have. Okay, so all this is a product rule. All right, now, if I would hang some integrals on it, the integral of this, I have to put a dx, and the integral of this, put a dx, and the integral of this, let's see what this says. This says the antiderivative of a product. Now, the product, one function is differentiated and one's not, but the end is a product. The antiderivative of a product equals the antiderivative of the derivative of a product. That's easy. That's just, as we said, that's f of x, g of x. So that is easy to do. And the other one, I have no idea how to do, but what you notice, I hope, is the thing switched on us. When you look at this, you have f and you have g prime. When you look at this, you have f prime and you have g. So if I could view this one as one of these is a derivative and the other is not, okay? I need to see an f g prime. So I need to view one of these as f and one of these as g prime. I've got two choices. So I'm going to view one of these as x. I'm going to view the other one, and you're going to see why I do this in a second. I can't see myself here. But I'm going to do, this is what people do. This is not exactly correct, but it's close. I'm going to see if I can rewrite that thing I have to do where I think of one thing as f, and I think of this really as g prime, but I'm writing it with differentials. In other words, this is the g prime right here, and this is the f, but I'm writing it as dv, and I'm writing this as u. So, but the point is that I'm taking this as the f, and this is the g prime, the cosine. So what does that make over here? That makes, what's f, if f of x is x, what's f prime? 1. So this is going to be 1, that's good. What's g if g prime is cosine? Sine. So the rule says this is x sine x minus the integral of sine x dx. If I took the time to write it out for you, we're at 19 after, this is what you get. The question is, can we now solve this problem? And if we can, and we're supposed to be able to, then we got the answer. So what we're going to be studying tomorrow is called integration by parts. And the idea is to have things we haven't been able to do before and substitution doesn't work. We're going to learn how to use the product rule basically backwards, shift a little bit. And the idea is when you have something you can't do, to switch it around to something you can do. And it's very clever. And it works for all kinds of stuff that nothing has worked before for. And see, the truth here is that there's billions of problems you guys haven't seen yet. We've looked at one little class of them, which is the substitution ones, and you haven't seen a bunch of others. That's just because you didn't think about seeing a bunch of others. You had trouble doing the ones you had to do. It turns out that integration by parts is another very important thing. I'm going to turn off the recording here.